back to the third day of the conference. So we're very happy to have Daryl giving his mini talk on properly convex manifold and generalized cusps.
Thank you. So a generalized cusp is a end of a properly convex manifold of a certain kind. I'm looking at the ones that are topologically the product of a torus and array. In dimension one, the generalized cusp, topologically, it's an annulus. It's the quotient of a properly convex domain in the plane by a group of affine transformations. There are three types. So the last time we saw that the polynomial is upper triangular with real eigenvalues, positive real eigenvalues. If you think about Jordan normal forms here, there are three possibilities: diagonal, a Jordan block of size 1, a Jordan block of size 2, or a single Jordan block of size 3. In the first two cases, there's a metric on here, a Hilbert metric, and as you go out into the cusp, have these circles, horror circles, and the length of the horror circles as you go out to infinity approaches, in these two examples, a curve whose length is log of 8. In this example, as you go out into the cusp, the curves shrink exponentially towards 0. In this case, the domain is in the positive quadrant. It's a set of points where xy squared is equal to 1. In this case, it's a set in the plane where y is bigger than negative log to base 8 of x. And in this case, it's a set of points where above the parabola y is a half x squared. If you look at these spaces in projective space, so the blue, we've got this projective line at infinity. And in this case, the domain, projectively, there's this segment called the boundary at infinity of omega. And the boundary of omega comes in transversely to it. So this domain has corners where the boundary of the domain is not C1. In this case, the domain in projective space is a curve which comes in orthogonally at the end, transversely at the end corresponding to the y-axis. But the end corresponding to the x-axis, it actually comes in C1. So this curve is below the x-axis. It gets further and further away, but very slowly. And as a result, when you look projectively, this curve comes in. It comes in C1, but it's kind of the second derivative is infinite. And in the last example, well, you've got the round disk in the projective plane. So those are three examples. The moduli space of, so what is the moduli space? In general, it's a set of marked generalized cusps up to projective equivalent. So you've got one for every dimension. So in dimension 2, the marked moduli space can be identified with a subset of the Euclidean plane, the subset of points where coordinates y1 and y2 are positive, and the y2 coordinate is bigger or equal to the y1 coordinate. Points in the interior of this region correspond to cusps of type 2. Those are the ones with diagonalizable holonomy. The boundary of this region, these two arcs, correspond to cusps of type 1, where you've got a Jordan block of size 1, a Jordan block of size 2. And the origin corresponds to the single parabolic type cusp. There's a homeomorphism in this case from this subset Y of the Euclidean plane to this space. So this space, you can think of it as a space of developing maps up to equivalence. So this is some abstract topological space, but it's homomorphic to this subset of the Euclidean plane. And this is a homeomorphism. You give me a point, and well, I'm giving you here the generator of the cusp group. So this is a homeomorphism from this subset of the plane into this space that actually factors through a subset of the representation variety. In dimensions bigger than 2, describe a homeomorphism to the moduli space, but it probably doesn't factor through a subspace of the represent. You can't lift this to a map from the representation variety into the space of moduli. Shatter, if you have a question. The general situation is following. So if you have a generalized cusp, well, so this is some domain, properly convex domain in affine space. It's a set of points lying above a hypersurface that's strictly convex. It meets a projective plane at infinity. Well, it meets a projective plane at infinity in some simplex of dimension R, where R is the rank. So in the case of a surface, the simplex is dimension 1 when the type is 2 or type 1, and this simplex is dimension 0 when the type is 0. In general, the dimension of this simplex at infinity is the rank, and the rank is the maximum of the dimension minus 1 and the type. And the geometry, there's a Hilbert metric here, and as you go out into the cusp, asymptotically, well, you have some directions on here correspond to parabolics, some directions correspond to hyperbolics. As you go out, the parabolics shrink exponentially, and the hyperbolics directions don't shrink. There's an action of this group on this simplex at infinity. Usually that action isn't discrete, but sometimes it could be discrete. You could have that the quotient of this simplex at infinity is a torus of the appropriate dimension. And in that case, as you go out, what is happening in this cusp is these horotori, a tori of dimension n-1, but some of the directions are shrinking and it's getting closer and closer to a lower dimensional torus. The other dimensions are shrinking exponentially. In general, of course, it's group acting on this simplex to be not discrete, and so that picture isn't quite right. I've been focusing on the simplest case. These are so-called maximal cusps. These are cusps where the boundary is a compact manifold. And in that case, in general, the boundary of the cusp is homeomorphic to a closed Euclidean manifold. So the fundamental group is virtually abelian. And I've been focusing on the simplest case where the fundamental group is abelian and the boundary of a cusp is a torus. In general, there's a Margulis theorem here that tells you that the set of points in a manifold, properly convex manifold, where the injectivity radius is small, is virtually nilpotent. And so there's a notion of a cusp and the notion of a generalized cusp. A cusp is a generalized cusp with no hyperbolics in, only parabolics, or if you're working with orbifolds, elliptics. So a cusp in general is a quotient of a properly convex domain by a discrete group of parabolics, and that actually implies it's virtually nilpotent. A generalized cusp, you allow hyperbolics as well. So in these lectures, I've been focusing on the simple case of where the boundary of the cusp is compact, a so-called maximal cusp. A cusp in a hyperbolic manifold is called standard, and it has a Euclidean structure, and the Bieber-Bach theorems tell you that the fundamental group is virtually free abelian. A more interesting case is when you take the symmetric space for SLNR. So you can realize that projectively, if you take the space of positive definite quadratic forms on Rn and projectivize it, that gives you a properly convex domain in a projective space of this dimension. And SLNR acts on this domain. If you take the discrete group consisting of SLNZ intersect the upper triangular unipotent matrices, this is a group of parabolics. And so the quotient of this domain by this group is a cusp according to this definition. And so there are many possible Jordan normal forms for parabolics. In fact, there's a theorem of Malchev that every torsion-free finitely generated nilpotent group is a subgroup of some GLNR. And so it follows that actually every such group is a fundamental group of a cusp in this sense, a discrete group of parabolics, which makes the following theorem somewhat surprising. If you have a properly convex manifold and you have a maximal cusp in it, then in fact it's standard. None of these exotic parabolics occur. It's standard, meaning that it's actually projectively equivalent to a cusp in a hyperbolic manifold. In particular, the group is virtually abelian. Here's an example of a kind of exotic cusp. So there is a strictly convex domain with a group of parabolics acting on there that give you a cusp. And the fundamental group of the cusp is not virtually abelian. It's virtually nilpotent. It's in this example, it's actually the Heisenberg group. And here's a homomorphism. The Heisenberg group is the upper triangular group in SL3R, the unipotent upper triangular group. And here's a homomorphism from SL3R into SL10R. And there's the homomorphism. And so if you restrict that homomorphism to the integers, you get a discrete group of parabolics acting on a strictly convex domain in RP9. And the fundamental group of this cusp is not virtually abelian, but it's the Heisenberg group. I should say this example has been greatly generalized by Balthazar Flagel. Parabolic in this example, yeah, parabolic means all the eigenvalues, it's unipotent, all the eigenvalues are on the unit circle. So no hyperbolics, yeah. Okay, so I want to sketch a proof of the theorem that maximal cusps in properly convex manifolds are standard. And this uses a characterization of ellipsoids due to Saucy-Mettu. And so her theorem is if you have a strictly convex domain in projective space and a point in the boundary, and suppose you have a group of projective transformations that map this domain to itself and map this point to itself. So in other words, an elementary group. And it acts simply transitively on the boundary with this point removed. And this group has got no hyperbolics in it. In other words, all the eigenvalues are on the unit circle. Then, in fact, the closure of this domain is an ellipsoid, and this group is conjugate into PON1, the group of isometries of hyperbolic space. And once you know that you get this Carrere mention. So this is a theorem about strictly convex domains, but you get the result about properly convex manifolds that every maximal cusp in a properly convex manifold is standard. And so there's a bit of work to go from strictly convex to properly convex. If you're interested in the details, it's in this paper. I'm going to sketch an alternative proof of Saucy-Mettu's theorem, which is to be found in this paper. So you can prove her theorem by induction on dimension. For surfaces, it's obvious. So how do you prove something like this? Well, so we've got going to have some. Like, who knows what the dimensions are? N+2, N+3, I get confused. But anyway, so we've got some domain, according to this theorem, a strictly convex domain, and this point is at infinity in the affine space, and the domain is the graph of some function above this coordinate hyperplane. And by induction on dimension, we know that if you reduce dimension if you leave out one of the coordinates, that this is actually an ellipsoid, that the boundary of this domain in this codimension 1 slice, well, it's a paraboloid. The x0 coordinate is half the square of the norm of the vector in the horizontal hyperplane. So in this codimension 1 slice, you know that. And in addition, you know that the group acting on this codimension 1 slice is standard. So what it means to be standard is that it's actually, if you think about the Lie algebra of this group, this is the Lie algebra, and so you exponentiate that, you get the standard group of parabolics, and when you take the orbit of the origin under that group, you get this paraboloid. And then the point you notice is that when you exponentiate out this group, the last column in this matrix, when you exponentiate it out, well, it's the orbit of the origin. So the last column, when you exponentiate out this, the entry here is this function f. And so the point is that inductively on dimension, we know in this codimension 1 slice, the group we're dealing with is standard. And so when you add in the extra dimension, well, I've put in the extra dimension in a funny place. So here I've left out, in the inductive step, we're working in one higher dimension, and I've left out in these coordinates the penultimate vector, the n+1th vector. And so to do the inductive step, you kind of know that the group is going to be the exponential of some Lie algebra of this form. You know what the stuff all here is. You don't know what the stuff in this column is. You know there are zeros here because we know the holonym is upper triangular. And you don't know what this entry is. So inductively, you know the holonomy is of this form. And what we're seeking is, well, the orbit of when you exponentiate out this group, the last column is going to tell you the function that we're looking for. And now the observation is that, so we've got to take the exponential of this matrix. And the observation is the fourth power of this matrix is 0. So the exponential map is this cubic polynomial. So that means when we exponentiate out this matrix, whatever it is, well, it's going to have polynomial entries of degree at most 3 in these variables, the x's and the t's. And the fact the boundary of this domain is strictly convex actually tells you this cubic polynomial is going to be degree 2, because x cubed isn't strictly convex, but x squared is. So with a bit more algebra, you can discover that this is exactly standard. So that's a sketch of the theorem. And so from that, well, with some other arguments, you get that maximal cusps in properly convex domains are standard. So last time I gave the classification of generalized maximal cusps with free abelian fundamental group. I said what you do is, well, there's finitely many Lie subgroups of the affine group. There's something called the type, which is an integer between 0 and the dimension of the manifold you're working with. And depending on that dimension, you write down this Lie group here, which is isomorphic to R to the n, this abelian group. And then you take a codimension 1 subgroup in here corresponding to a certain homomorphism from this group to the real. So you choose this homomorphism psi, and it's not any homomorphism. It's actually got to send the standard basis here to non-negative real numbers. And the number of non-negative real numbers is something called the, actually, I think that should be T for type. And then you take the kernel of this homomorphism, and that's this codimension 1 group. So this is a codimension 1 Lie group. And then a lattice in here is what gives you a generalized cusp. So I want to prove this classification result. And the key observation is that in this situation, if you project onto the coordinates corresponding to this diagonal matrix in the top left corner, that's projection of the domain onto a simplex, and the preimage of a point in the simplex is a standard horoball on which you've got this unipotent group acting. So the idea of the classification proof is to say if we have a translation group. So let me remind you, what is a translation group? A translation group is a group of affine transformations with the property that if you take the orbit of a point in Euclidean space, it's a properly embedded, strictly convex hypersurface. So we want to know that every translation group is conjugate to one of these. And the idea is to prove that, well, we have this picture. Shout out if you have a question. So this is the classification theorem. Okay, so the deal is we've got this subgroup T of the affine group. It is isomorphic to R to the n minus 1 as a Lie group. The orbit of a point is this codimension 1 strictly convex surface in affine space. And sometimes T will denote a group, and sometimes it will denote the image of a homomorphism onto that group. So it's either a homomorphism from R to the n minus 1 onto a subgroup, or it's the image of that. So the idea of the proof is if somebody hands you a translation group, well, you get this convex subsurface, you get a domain, and we want to prove there is a linear map from Euclidean space to a smaller dimensional Euclidean space that sends this domain to the interior of a simplex. And the preimage of a point is a horoball. So that's what you want to prove. And last time, I explained that what we know about T is that it's conjugate to a group of upper triangular matrices with positive entries on the diagonal, positive weights. So we know that, well, there's a collection of positive weights. The number of weights I've called T plus 1. So, right. So there's a difference between thinking of a group, a projective group and an affine group. And when you think affinely, the number of weights goes up by 1. The number of, so that's why there's T plus 1 here. Anyway, so we've got this affine group, and there's some number of distinct weights. So I've called the number of distinct weights T plus 1. So these are homomorphisms from the translation group onto the multiplicative reals, the positive multiplicative reals. And corresponding to these weights, we have a decomposition of V, the vector space. So V here is, V here is the space we're projectivizing. So V is R to the n plus 1. We have a decomposition of V into the generalized weight spaces. So there's T plus 1 of them. And if we restrict, so each one of these subspaces is preserved by this group. So if I now think of T as a homomorphism, T preserves each one of these subspaces. So this homomorphism is a direct sum of homomorphisms onto these subspaces. And each homomorphism is, well, it's the weight times a unipotent representation. So rho 1 is some homomorphism, which is, well, it's upper triangular with 1s down the diagonal, and then we've got this weight in front of it. So what we know about T is that it's block diagonal, and the blocks are of the form of weight times this unipotent thing. Okay, so what we want to prove is that all these blocks have dimension 1 except the last one, and that the last weight is 1. So to do that, we want to produce a linear map from Euclidean space of dimension n plus 1 to Euclidean space of dimension t plus 1. And what we're going to do is each one of these vector spaces, I mean, I've written, there's a basis where the holonomy is upper triangular. If I take the last vector in each one of these vector spaces and call that W, so I'm going to get t plus 1 vectors W1 up to WT plus 1. It's the last vector in each block. This is a subspace of V. If I take all the other basis vectors and that's a subspace called U. And the point is that the subspace U is invariant under the group gamma because this thing is block upper triangular. So we get a decomposition of V as a direct sum of U and W, and U is mapped to itself. So that means that this homomorphism induces a map from the quotient of V by U to itself. And of course, the quotient of V by U, we can think of a W. So we get this representation gives an induced representation on W, and it's diagonal. I mean, all it's doing is it's picking out the weights. So this gives us a map then from Euclidean space from V to W, where we quotient out by U. And then in the projectivization of this vector space W, we've got the basis vectors, and there's a simplex, the positive linear combinations of these basis vectors. And because these are positive numbers, this simplex is mapped to itself by the induced map. So we've got this group gamma acting on this domain. We've got projection onto this subspace, this space W. The action of T on this domain covers an action of this diagonal group on this simplex. If you take the preimage of a point in this simplex, well, that's going to be the intersection of a domain with a projective subspace. And that, if we take the stabilizer of that projective subspace in this group, I've called that subgroup T sub K, K for kernel. We've got the kernel of the map from T to T star. That group is unipotent. So it now follows. So we had the original group was acting simply transitively on the boundary of omega. This subgroup PK is therefore acting simply transitively on the boundary of this subdomain, which is the boundary of the fiber. And so the result about ellipsoids tells us that the action of this subgroup is standard. So in particular, the action of this group TK is a single unipotent block. Now, if you think about it, what is this action TK? Well, it's made up of, it's basically this, where you leave out the last vector in each one. So that tells you then that actually all these blocks are dimension 1 except 1, and you can order things so it's the last block that's not unipotent. So you've got these blocks are size 1. This last block is a standard unipotent block. And then because we're going to work projectively, you can divide everything by this weight and turn this weight into 1, and all these other weights become the weights they were before divided by this weight. So you've reduced to the case where this weight is 1. This is a standard unipotent block. These are all one-dimensional. And you're pretty much done. The only thing you've got to do is some algebra to argue that the entry in the top right corner is given by a linear function of the kind I said. The psi's are actually positive, which follows from the fact that this domain, the boundary of the domain, is strictly convex. So that's the idea of the proof, yeah. Yeah, no, this domain, the interior of this domain maps into the interior of this simplex. I mean, you take a point. Yeah, so right. So I mean, there's an argument actually, right? So I'm missing out many things. So one of the things you prove is that except in the diagonalizable case, we can assume that in the special case where all these blocks have got size 1, the theorem's obvious. The thing's diagonalizable, it's easy to do. Except in that case, you can argue that this map is surjective onto the interior of this simplex, basically using the fact the boundary is strictly convex, and so the image is going to be an open set in here. And it's a group invariant open set, so it's got to be the whole interior of the simplex. Yeah, there's a lot of details I'm skipping, and the details are in the paper. I mean, I'm just trying to give you the Are there any other questions on that, by the way? So what I'm going to talk about next is the classification. So I want to describe the moduli space of generalized cusps, and to do that involves invariants classifying generalized cusps. A standard cusp in a hyperbolic manifold is described by saying it's a Euclidean torus up to scaling. So it's given by a Euclidean structure on a torus up to scaling, or if you like, a similarity structure. A generalized cusp is given by data as well. The data consists of a Euclidean metric on the boundary defined up to scaling. What I talked about last time, it comes from the second fundamental form, plus extra data. And so there are various ways of giving that extra data I want to explain. So, so what we've got here is a strictly convex surface boundary of omega in Euclidean space, non-compact. And we've got a group, a translation group that's acting, a group of affine transformations acting simply transitively on this surface. From that information, you can get a quadratic polynomial and a cubic polynomial. How do you do that? Roughly speaking, what you do is you take the tangent plane, so you take a tangent plane to a point B on the surface. You then think of this surface as a graph lying above the tangent plane. And so the height is a function of the coordinates in the tangent plane. Because it's tangent, the constant term is 0 and the linear term is 0. There's a quadratic term and a cubic term. The quadratic term and the cubic term are something called the shape invariant. Actually, they're only defined up to scaling. So the shape invariant is a quadratic polynomial plus a cubic polynomial defined up to scaling. And the actual definition, I mean, I said what you should do is you should take the 3-jet of the graph of this hypersurface above this plane. But that isn't quite what you do. You need to get something invariant. So what we've got here, V is a vector space of dimension n-1. It's so T is the image of a homomorphism from V, that is, as a group, it's R to the n-1. And you pick a affine map tau so that the preimage of 0 under the affine map is this hyperplane. And the affine map value is positive above the hyperplane where the domain is and negative below. So that's what tau is. And then we've got the orbit map. So this domain, the boundary of this domain is the orbit of a point under this translation group. So this translation group is given by a homomorphism from the vector space V, R to the n-1 to T. And that homomorphism is rho. The orbit map sends a point in V to the point you get in omega by moving the base point B by the image of V under the representation. So this is the orbit of B under this group. And so there's this function H, which is evaluate this affine map on what the orbit map does. So the orbit map is kind of, if you like, it's parameterizing the boundary of U, and then we're taking tau of this. So H is this map, and it's not a map from the tangent plane, it's a map from this abstract vector space we're using to parameterize the translation group. And you can think of this map as describing the height of a point on omega above the tangent plane, but a certain point in the tangent plane, not the point you're thinking of, but the point given by this representation. And the point about making this definition is that it's obvious that when you make this definition, the 3-jet you get is independent of choices. Well, it's independent of choices up to scaling, because this affine map, you could rescale it. So out of this, you get a quadratic and a cubic. The quadratic you get is the second fundamental form of the surface. I talked about that last time. And you get a cubic. And so this is something called the shape invariant. And so it's a quadratic polynomial and a cubic polynomial, and that uniquely determines the cusp, the generalized cusp. So, okay. So this is data. There are different ways to classify a generalized cusp. One way to do it is, if you have a generalized cusp, it's uniquely determined by the projective class of the quadratic and cubic, what we call in the shape invariant. It's also characterized by a pair of things. The pair of things is the Euclidean metric on the boundary up to scaling. So this beta rho is the similarity structure on the boundary. So you take the similarity structure on the boundary together with the character. So what do I mean by the character? Well, we've got a representation of r to the n minus 1 to the affine group, and we can take the trace, we can take the character of that representation. So that's what chi rho is. It's the character of this affine representation. So the pair consisting of the metric and the character is called the complete invariant. That determines the cusp up to equivalence. Instead of taking the character, you can take the weights. So this is these entries down the diagonal are the weights of this representation. They're functions on the group. Actually, I'm going to take their logarithms. In other words, I'm taking the weights in the sense of Lie algebra. So each one of these diagonal entries, its logarithm corresponds to a weight on the Lie algebra. And these are linear maps. I mean, the weights are homomorphisms from the Lie group to R. The Lie algebra weights are linear maps from the Lie algebra to R. So we can think of those actually, these Lie algebra weights are actually elements of the dual vector space. Now, the second fundamental form puts this metric on the vector space V up to scaling. So corresponding to these weights, which are dual vectors, there are vectors that are dual to them. So we've got the weights, and then we've got these vectors that are dual to the weights. So they're called they're the dual weights. So there's no particular ordering on these weights or these dual weights. So we want to record these weights and these dual weights up to permutation. So the symmetric product of a space means you take n copies of the space, the Cartesian product of n copies, and quotient out by the symmetric group. That's called the symmetric product. And so these weights up to permutation are an element in the symmetric product of the dual space. And the dual vector, well, the vectors corresponding to them are elements in the nth symmetric power of the vector space. Now, the cusp is the quotient, you can identify the cusp as the quotient of V by this discrete group gamma. So that means you can actually think of the dual vector space V star as the first cohomology of the cusp with real coefficients. And of course, you can think of the vector space V as the first homology of the boundary of the cusp with real coefficients. So you can think of these V's as homology classes, one-dimensional homology classes on the cusp, and you can think of these as one-dimensional cohomology classes. So another invariant, complete invariant of the cusp is a similarity structure together with these cohomology classes, or if you prefer, the similarity structure together with these vectors. So in the introduction, I said, here is a generalized cusp in dimension 3. I drew a parallelogram, and then I drew 3 vectors. And these weren't any three vectors. So these are, this is a parallelogram. So that's giving me a similarity structure. And then these three vectors had a special property. And the special property they have is that if you take a pair of distinct vectors, their inner product using the metric, the seconds fundamental form, is always the same. It's a certain negative constant. So depending on the cusp, there's some positive number var pi. And the inner product of every pair is negative that constant. This is a strange looking equation, but it's got a very nice geometrical interpretation. So one possibility is that this constant is 0. If this constant is 0, that's just saying these vectors are orthogonal. Now, the number of vectors is 1 bigger than the dimension of the vector space. So if this constant is 0, at least one of these vectors is 0. That means one of the weights is 0. That means you've got a non-diagonalizable cusp. Any cusp that isn't diagonalizable, this constant is 0. And then these vectors, this equation is just saying these vectors are pairwise orthogonal. If you have a diagonalizable cusp, then this constant is not 0. And this strange looking equation actually has a very pleasant interpretation. You introduce, so this vector space V, r to the n minus 1, is parameterized in the translation group. You add on an extra dimension. You've got an inner product beta on this vector space. You extend that inner product over this vector space by making this direction orthogonal and the unit vector of length 1. Then this equation is equivalent to saying that if you take the vectors vi and you add on this multiple of the vertical vector to them, those vectors are pairwise orthogonal in this bigger vector space. Why that happens, I do not know. It just comes out of the calculations that that's what's going on. Okay, so there are different sets of data to describe a generalized cusp. Are there any questions on that? Yeah.
It's just from matrix.
Yeah. So yeah, the top left corner is diagonal, and then the VI. If you do it, well, if you assume that, yeah, it's basically the diagonal part of this matrix in the top left corner. I mean, admittedly, you've precomposed the standard representation with some element of the special linear group of V, but yeah, basically it's given by the directions of the weights in the lead group, if you like. So yeah, so how you should think of these is that as you move around in the torus, there's some each of the eigenvalues is changing. And the rate that a certain eigenvalue changes, as a certain weight changes, you go in a direction, depends on how big that vector is. It's roughly what it's saying. Yeah.
Not too big, but I mean, we can think about the more degree. For example, S4V or S5V.
Oh yeah, oh yeah. So why? Okay, you're saying why don't you have to think about higher? Yeah. Okay. So right. So let me make a remark. So a strictly convex projective structure on a closed surface is given by a conformal structure on the surface and a holomorphic cubic differential. This is a theorem of Hitchin. This is somewhat reminiscent because it's saying that a generalized cusp is given by a quadratic differential and a cubic differential. Why you only have to take the cubic terms and not the higher order terms is a long computation, but it suffices that the cubic terms suffice. Yeah, does that answer your question? Yeah, so a lot of the proofs here, there's one basic point here. Everything is computable. I mean, at the end of the day, we're dealing with some very specific groups of matrices, and you can compute everything. I mean, it's algebra and it's elementary algebra, but there's a lot of it and it's pretty complicated, but you can compute everything. So you can compute you can compute everything. Okay. So, yeah. Yeah, SL3R, yes. Yeah.
Doesn't it really give that to you? Because you see the diagonal entries are, and you don't come up to
I should say, not entirely sure this stuff works for surfaces. I mean, but yeah, right, but okay, in a surface, so what's the data? I tell you a Euclidean metric on the surface up to scaling, 0 information. So if it's type 0, that's all the information you need. There is only one parabolic cusp. But if it's type 1 or type 2, you need to know the length of that boundary component, and that isn't given by the metric. The metric's only defined up to scaling. Well, the length of the boundary component comes from eigenvalues, and that comes from the weights, and that comes from this extra data. Does that answer the question? Yeah, and in fact, and the weights, there's either one of them or two of them, and that's telling you if it's type 1 or type 2. You can kind of reconstruct the representation. Actually, in that dimension, right, you can obviously reconstruct the representation from the weight. You've got the weights, and so you can just do it. Okay, how do you prove all this stuff? So the goal here is to sketch, so from this you can determine the topology of the moduli space of generalized cusps. Surprisingly, it turns out to be homeomorphic to a subset of Euclidean space. I say surprisingly because one might have guessed it would be non-Hausdorff, but it turns out actually, I'll tell you next time.